Hello and welcome to Lecture 2 in Using Newton's Laws in Phys 1101. And we're now going to deal with friction, which is really complicated. So this is the first of two lectures all about friction, and then we'll still have more issues to deal with friction in other lectures to come. So friction is really very poorly understood. There are a lot of people actively researching it, and there's a lot we don't understand about how to predict it, how to calculate it, and so on. We have some simple models that work a lot of the time. There are three types: kinetic, static, and rolling. And kinetic occurs when two things are sliding against each other, static when they are not sliding, and rolling, obviously, when things are rolling. And kinetic and static friction oppose sliding. They don't oppose motion, although you may have heard before that they do, but actually they can often be the causes of motion. Just think about this conveyor belt. If there was no friction, the boxes would be lying at the bottom of the conveyor belt, with the conveyor belt sliding along underneath. It's the friction force that's pulling these boxes up the ramp. So whenever two objects are in contact and they're slipping against each other, they'll each exert a kinetic friction on the other. And this kinetic friction will act in a direction that reduces the slipping. Now, you may have learned that kinetic friction always opposes the motion. And in simple cases, it does. But we'll see that that's not really accurate. But let's start with a simple case. If we just have a box sliding to the right across a floor, well, it's slipping on the floor, and so there'll be a kinetic friction. So, thinking about this in the usual way, the box is only in contact with the floor. There will be a long-range weight force due to the earth, there will be a normal force up due to the floor, and to reduce the slipping in this case means slowing the box down. And so the kinetic friction will act in the opposite direction to the velocity of the box. And if you add those up, the normal and the weight will cancel, and the net force will be back, and that will act to slow the box down. Let's again see an example where a friction doesn't oppose the motion. And again, conveyor belts are useful for seeing this. So let's suppose we have a box on this conveyor belt and everything's stationary, but then the conveyor belt starts up very suddenly and ends up going to the right at some velocity v. Then the box has to accelerate to the right and wind up also eventually going at v. Now, it'll accelerate with the belt if the surface is very nice and grippy, and then there will be a static friction. But if it slips initially, if the surface is a little smooth and the belt starts up very suddenly, then this will be a kinetic friction force. But either way, we know that the net force on the box must be to the right, because that's the way it is accelerating, right? It's speeding up to the right. And the only other force that can act on it that I haven't already got on this free body diagram is the friction due to the belt. And so whether it's a static or a kinetic, whether the box slips initially or not, that friction force is causing the box to speed up. It's acting in the direction of motion. Here's another very simple experiment you can do at your desk. Grab a book. Push it across the desk. Feel how hard you have to push it. You won't have to push it very hard. Now, press down on it, just down, with your other hand, and you'll find that with the hand that's pushing the book, you have to push much harder than you did before. So to understand what's happened, let's just look at the free body diagram. The only things in contact with the book are my hand and the desk. The desk is going to exert a normal and a friction. My hand is exerting something I'm calling F push. Note that that's just another normal force, but to avoid confusion with this normal force, I'm going to call it F push. And so I have the normal due to the desk, the friction back to the left, I'm pushing to the right, and the usual weight. And now when I press down with my other hand, so I'll drag this excellently drawn hand up here, now there's a new point of contact, and so there will be another force there which I'll call F press, right? I'm pushing with one hand and pressing down with the other. And so that introduces a new downward force here. Well, the book does not accelerate down into the desk, and so the normal force must have increased to compensate for that F press. And what we're seeing now, the reason it was harder to push the book is that it turns out that when the normal force increases, so does the friction. The friction turns out to be proportional to the normal force exerted by the same surface. We're now ready to write down an equation that we can use to calculate a kinetic friction, now that we know it's proportional to the normal force. And be careful, it's proportional to the normal force exerted by the same surface that's exerting the kinetic friction. So be very careful, keep track of agents, right? Which surface is exerting the kinetic friction that you're calculating? It's proportional to the normal force exerted by that same surface. And the equation for it is like so. The friction is just this mu k, which is called the coefficient of kinetic friction, times n, the normal. Notice there are no vector symbols in this equation. This is a statement about the magnitudes of these forces. If you were to put vector symbols on it, it would be wrong, because the normal force is perpendicular to the surface exerting it, and this friction force is parallel to the surface, and so they can't possibly be pointing in the same direction. This symbol mu k stands for this coefficient. Note, it's not a force. Fk, the friction, is a force. Mu k is not a force. It's a coefficient. If you do a dimensional analysis, the friction is a force, the normal is a force, and that tells you that this coefficient is dimensionless. It has no units. So don't mix it up with a force. It's a thing you use to calculate a force. And it's a property of the two surfaces that are sliding against each other. Since coefficients of friction are properties of the two surfaces sliding, you often look them up on tables if you can't measure them directly. And so you see, if you change one or the other surface, then the coefficient of friction is different. And if you compare these tables that I found in various sources, you'll see there's a fair bit of discrepancy between them. As you'll see in the lab, coefficients of friction are incredibly unreliable. So for some reason, everybody wants to quote them to two significant figures. That's just nonsense. You might be able to say this piece of steel against that piece of steel today gave me this coefficient of friction to two significant figures, but come back in 2 days when the temperature and humidity in the room have changed and there's a little more dust on the surfaces, and you'll measure a significantly different coefficient. Let's work an extended example that'll bring a bunch of these ideas together. So we have a wooden box sliding down a wooden ramp, 5 kilogram box, initially going 2 meters per second, and it's a pretty steep angle on the ramp, 40 degrees. And I've started the free body diagram here. The only thing this box is in contact with is the ramp. So all we should have is a normal force perpendicular to the ramp and a friction force opposing the sliding, means up the slope in this case. This is a simple case where the friction does oppose the motion. So the net force, when we're going to have to think about this, what we want here is the acceleration of the box. And we don't know. We don't know whether the box is speeding up or slowing down. I suppose it could be going at a constant speed. Let's guess that the box is slowing down. That would mean that F net points opposite the direction of motion, or up the slope. We need to set axes. So we've got 3 tipped vectors and 1 untipped. So we will do a lot less breaking into components and make life generally easier for ourselves if we tip the axes like so. Perhaps the next thing to do is to break the weight into its components. So to save time, I've done that down here. Here are our axes, W and its components. There's a 40-degree angle here. So that makes this a 50-degree angle in here, and that means there's a 40-degree angle down here. And so Wx is the opposite, and so it gets the sine. Wy is going to get the cos, and note that these are both negative, right? If you compare them with the directions of the axes, both of those components are negative. So now we can start translating our free body diagram into a statement of Newton's second law for the object. So that just means adding up our x components of forces, adding up our y components of forces, and setting them all equal to ma. So in the x, we've got Fk directly along the axis, and so it just write down Fk, and we've got our x component of W, which remember was negative mg sine 40 degrees, and that's going to be m times the x component of A. And in the y, we've got the normal, and we've got our y component of the weight. And F net is along the slope, right? If F net had a y component, then this box would either be leaping off the surface or burrowing into it, and neither of those sounds too plausible. That's 0. Now I know you're probably very tempted to start plugging in numbers, but it's not time. I find something that really helps students is to stop at this point and count their unknowns by circling them. So AX is what we're looking for. It's certainly an unknown. We don't know the friction. And you might be tempted to think that n is just mg, but remember, we always have to solve for it out of Newton's second law. You may see we can do that easily, but we haven't done it yet, so that's an unknown. M is 5 kilograms, g will use 10 meters per second squared, and you might think that these are unknowns because you have to plug things into your calculator, but you don't have to solve an equation to get them. They're just numbers, and your calculator knows them even if you don't, so those are knowns. And look, we've got 3 unknowns, but only 2 equations. So it doesn't matter how you manipulate this, there's no way to solve it. We need another equation before we can solve, and we have another one. It's the one we've just seen. Okay, and now if you look at that, it's got these 2 unknowns in it, but those are not unknowns we already had, so we haven't added any unknowns. In mu k, this is wood on wood, and so that's apparently 0.2. Right? We'll go with what the table says. So now we've got 3 equations and 3 unknowns. We can solve that. So I'm going to plug that up into here, and I'm going to flip it around because we're solving for AX. So this equation now looks like this. And note that I still can't solve that because I don't know n or ax, but I can solve for n out of here. And now plug that into here. And we've now saved ourselves a whole lot of work because we're only going to have to plug into a calculator once. And look, we've got an m in every term, and so all those masses just cancel out. So in the end, now it's time to sub in because we've got AX isolated, right? So we've got 0.2 times 10 meters per second squared times cos of 40 degrees minus 10 times sine of 40 degrees. And a quick unit check. Look, we've got meters per second squared and unitless everything else. So this comes out in meters per second squared as it had better. And I've already plugged that into the calculator to save time. You see it's negative 4.9 meters per second squared. Negative 4.9. Does that mean it's slowing down, right? A negative acceleration slowing down? No, hold on. Remember, we set F net up the slope speculating that this was slowing down. If we'd got a positive answer, that would mean it was pointing in the positive x direction as we guessed here. But it's not, it's negative. And so that's telling us that the acceleration is 4.9 meters per second squared down the slope. That means this is speeding up.